Hello everyone, welcome back. In previous session we talked about diffraction probabilities for simple cubic, body cubic center, body centered cubic, face centered cubic crystal structure, FCC, BCC, simple cubic, SC. We said that diffraction will occur if the h square plus k square plus l square is set of numbers for each of them. Now we're going to solve some examples this week that will mainly be for exam. We'll start with an easy one, then we're going to solve some hard examples. The example we're going to solve is 3.66. We have an XRD pattern. We have 4 peaks. If the pattern is given to us, means that we have for each peak 2 theta diffraction angle. We have it. So if we read those angles, for example, this will be 43 something, it's going to be 50 something, 70 almost 4 or 75, 90 point something. Now reading the angles from the graph need a precision, because if you are not accurate with the angles, the result that you're finding it from the analysis will be different, and we're going to see it in this example. Why? Because the value that they have them, they are not accurate enough for the result to come exactly close to each other. So we're going to see what will happen if you're not accurate with the angle. Now, if I'm going to give you an example or a problem to solve a question, I'm giving the angles at least with 3-4 digits, 4 digits, so that the result at the end will come exactly similar. I mean, what is the result we're looking for? We're going to explain in the example why the result has to be exactly similar for the calculations. Now, some information. We said each peak associated with a set of plane. For example, this is for a set of plane, this is another set of plane, this is another set of plane, this is another set of planes. So each of the peaks represent a set of planes. Call them equivalent planes, family of their families, basically, or equivalent plane and their families. So each of them, they have 2 theta, they have Miller indices, and since it's a plane, it has O1 interplanar spacing, DHKL. Remember, we said interplanar spacing, the space between equivalent planes, we call DHKL. For each of the peaks, we have different DHKL. Now let's read the question to see what does it say. Figure 3.5 shows the first 4 peaks of the X-ray diffraction pattern for kappa. So the element we have it is kappa. Now remember, the pattern that I will give it to you, it's only for one element. It's only for one element. This is important. Why? Because it's going to give us, well, we have to know some information. Since it's for one element, for this pattern, or I can say for each peaks, the crystal structure is the same. So we don't have different crystal structure for each of the peaks here. Why? Because it's only one element. It's only one element. So all the peaks, they have the same crystal structure, or is the same crystal structure for each of the peaks. Now this example is easy. Why? Because the crystal structure is given, telling us that which has an FCC crystal structure. That makes the solution easy. Why? Because we know the crystal structure. Well, we have a wavelength which is lambda 0.1542 nanometer. Then the question will be index and finding their planes HKL for each of these peaks. So we want to find for each of the peaks the plane indices, which is HKL. I mean, this represent which plane, this represent which plane. Then listen, this one is part A. Part B, determine the interplanar spacing, which is DHKL for each peak. Yes, again we say for each of the peaks. Why? Because each peaks, they have different HKL, then the interplanar spacing will be different between them as well. Sorry, between the interplanar spacing with difference for each of them. The last part will ask, determine the atomic radius. So we want to find atomic radius, and then we will compare it with the table. We have a table, there is a table, we have it. For example, we have kappa here, kappa is here. We know the atomic radius is supposed to be 0.128. To see if we can get exactly this 1.28 from the calculation, we will see it in a bit. So we're going to solve this one. By solving means that we have to write down the peaks. We have 4 peaks, so we're creating a table. We'll create a table, then we will see what we need further. Now, in order to create a table, let's say we have something like this. This is the table, we have it here. Now we have 4 peaks, and those angles found by using ruler and scale to see exactly how much is this angle here, because the peak basically means that this is the angle that will be taken here. This is 2 theta, this is the third one, and this is the fourth one. So we have 4 2 thetas. It's not going to be 90 point something. So those angles in this example calculated by using, or found by using ruler and some scaling in order to get at least accurate angle. They are still not accurate enough. Why? Because they're only one digit given. You're gonna see at the ends to see what will happen due to those insufficient accuracy of the angles. Then you'll see the result at the ends will be different. Now, since we know the crystal structure is FCC, and that's basically tell me that we know that h squared plus k squared plus l squared. If you remember, for FCC we said that the first peak will be 3, the second one will be 4, the third one will be 8, the fourth one will be 11. If you don't remember those numbers, check the previous video when I explained the sum of the square of Miller indices. We had the pattern for simple cubic, for BCC, for FCC. Since we know the crystal structure here, the crystal structure is given, so I know those numbers. This is what's going to help us to find the rest of the solution. Well, we said that this one depend on this, yes, because we want to find HKL depend on this number. Remember the rule for FCC? The rule for FCC, what was it? We said for FCC crystal structure, HKL, we said that all even or all odd. Sorry, off. This was one of the rules for FCC, that HKL for the FCC, that's going to be the planes that will diffract, they should follow this rule. All the Miller indices even or all of them odd. So if you want to say that if you want to find plane for this one, in order to get 3, the first plane will be 1, 1, 1. Why? Because, sorry, one, 1, 1. Why? Because 1 square plus 1 square plus 1 square will be 3, and all of them are odd. Then we did this one in the previous example. You know that this will be 2, 0, 0. The other one will be 2, 2, 0, and the other one will be 3, 1, 1. So those are the planes that we have them: 1, 1, 1, 2, 0, 0, 2, 2, 0, 3, 1, 1. The planes they're representing. So if we have the pattern, I can simply say that the first one is 1 1 1, this is 2 0 0, this is 2 2 0, and this plane is 3 1 1. Those are the Miller indices, which is part A. It says index, i.e. give HKL indices for each of these peaks. So we found the indices. How we found it? Because we know its crystal structure. We know the crystal structure. We know its crystal structure. So since we have FCC crystal structure, we know the sum of the square of the Miller indices will be 3, 4, 8, 11 for the first four peaks. So 3 for the first peak, 4 for the second peak, 8 for the third peak, 11 for the fourth peak. Then we know how to get the HKL by following the rule for FCC. Now, in order to find the DHKL, it says part B, determine the interplanar spacing. Well, DHKL, we have the equation says that there's two equations that we can use to find DHKL, to see which one will be used. So if I write DHKL, sorry, so I have two equations. First is A over root h square plus k square plus l square. That's the first rule. Now can we use this one? If you see that we don't have A, yes. Now we have the h square, the sum of the Miller's indices, square Miller indices, but we don't have A, so we cannot use this one. We'll check for the second equation, which is n lambda is equal to 2 DHKL sine theta. Well, we have theta, we have n is 1, the order of reflection, if it's not given, it's 1, the wavelength, we have it, and theta for each peak, we have it, so we can find the Miller indices. So if this is the interplanar spacing. So if I rearrange this one, DHKL here, DHKL will be equal to n lambda, well, n is 1, so I can just simply say that directly, lambda n is 1, we write to do 1 times lambda over 2 sine theta. Well, we can calculate them. Well, because we have lambda, lambda is given to be 0.15, if it's 4, let's see, so lambda is given 1542 divided by 2 times sine. Don't mind the way I'm writing it here, this is something different. So if you do the calculation, you'll get this answer. So then you can do the rest for the rest of the other peaks. Remember, for each peak you're going to use what? You're going to use the theta, so I have 2 theta, I made them theta, half of them, divided by 2, I get theta, then I use theta with the I only need what? Lambda over 2 sine theta, we get all the DHKL, that we have. Now those are the DHKL. If you want to calculate A, you're going to calculate A from where? You're going to calculate A from this time, from here. Since we have, now we found the DHKL, and we have those values, so I can find A. A will be DHKL times the root of this value. Now we have them, So you can just simply say that, okay, A will be this one times root of this one. So if I can write it this, if you calculate it, so will be this one times root of this one. Now, what do we expect for all the other A here? We expect them to all of them have the same value. We expect all of them to have the same value. But look at the difference we have them. 35803, 35949, 3606, 36037. The difference in A we have them, it's due to the angles that we have them here. Due to the angles that we have them here. Why? Because we said that we have one element. Yes, the pattern that we have it here, it's for kappa. And kappa has an FCC crystal structure. And if all of the peaks they have the same crystal structure, it is the same element, so you're expecting A, it's everywhere the same. A is constant, the lattice parameter. If you remember, if it's one crystal structure, we have it here. If it's one crystal structure, then A is constant. A is constant. But why do we have difference here? Why do we have difference here between the A's? This is mainly due to the angles. Due to the angles. This is not going to happen in the exam. When I give example, you'll see all the A's will come close. Close means that at least 4 of them, 4 digits will be equal. There might be difference in the fifth. Very small difference. I'm going to show it to you in an example to see what will happen if you have those angles in full detail. For example, if this is something different, sure, those are going to change as well. Maybe they're very, very small. For example, if it's just 1 digit, look, it's going to change. So you don't know exactly the digits here, how much they affect, unless you'll find A. Why? Because they're in nanometer, they're small numbers, so it will affect them. But in the exam, we're going to see all of them equal values. Why? Because we have one crystal structure, which is supposed to have one A. Even R is the same manner. We have with kappa and radius of kappa, it's going to be the same. Let's find the radius. How do you find the radius? We know it's FCC crystal structure, yes? Since in FCC crystal structure, A is equal to 2 root 2r. We know this one from FCC crystal structure, 2 root 2r. And if I want to find r, will be A divided 2 root 2, so I can find it there. Now again, r, all of them supposed to be the same, or at least very close to each other. But you see it here, 126, 127, 127, 127. They are close, yes. 75, 74, 71, 65. They are close, but still not close enough. Again, the reason why the angles gonna make this difference. Now, in order for me, I recommend you to prepare things for me in table. So when I give diffraction, we prepare the result, the analysis in table, the way that you see it here. But in order for someone to understand what you've done, you take the first peak and you show the calculation of how you find all of them. So you will do one calculation. For example, we say first peak, then you're going to calculate, for example, the DHKL. You will show it how did you find DHKL. You'll write the equation, you'll find this answer with calculation. So we need calculation for first peak. We need calculation for first peak is required. So DHKL, you'll find it, A, you'll find it, R, you'll find it. So you will do this calculation. I mean, which equation you used it, how did you find at least this number, this number, this number. Then the rest of the others, no need to show the calculation. Just fill the table, and that will be enough for us. I'm not gonna calculate the time required to solve this based on Excel. I calculate the time based on normal calculator. You're going to use calculator to find all of these values in the exam. So now we have the value for R. This is the value for the HKL, the interplanar spacing. Now how do we know that if those numbers are correct? Well, I've done them with the program, but if you do it with calculation, you should know some information. DHKL decreasing when the peaks increasing. The reason for that one, because when finding DHKL is lambda over sine theta, 2 sine theta, and sine 90 will be 1. So when the angles come closer, the value basically will be smaller. When the angle goes closer to 90, or around above 90, then the DHKL basically is decreasing here. A and R, you're expecting it to be the same. Why? Because we have one crystal structure and one element, then we shall see similar result for A and R. Now if you check the table, look at the radius we found, the 127.5, so between them, yes. But in the table we had what? In the table for the kappa, the atomic radius is 128. Now the difference that we have, we got 75, 72, 70 something, 65. The result is close but not close enough, and the reason is due to the angles. Now again repeating this question, we knew the crystal structure, that's why we could simply start with the h square plus k square plus l square, then find the planes and find the rest of the requirements based on the plane. Now we're going to solve an example that we don't know the crystal structure. So if you don't know the crystal structure, how would you find the crystal structure? Will be new information. Then we're going to solve 2 examples, will be enough for the exam. Thanks for watching.